Welcome to ECE 3270, Introduction to PLC Programming, Lecture 3. Today we're going to be talking about programming with math instructions in ladder logic. So we are going to have a connections to industry little intro, then we will get into the instructions, and finally we're going to end with a practical demonstration in the Logix platform. So, as promised, here's our industry connections intro. Today we're going to be discussing joining. So, joining is a general term that refers to joining two materials. There's a lot of different ways to go about that. Welding, of course, you can attach using some sort of fastener, but there's also typically, when you hear someone refer to a joining station or a joining machine, a lot of times what they're referring to is a joining by force machine, so a pressing operation, where one object is pressed into the other. Typically, it's some sort of cylindrical or circular object being pressed into a hole, and the hole is usually slightly smaller in diameter than the object which is being pressed into it. And since the object is slightly larger than the hole, when you put enough force to push it into the hole, the squeeze of the hole onto the object holds it in place. That produces friction, which holds it in place. So we're going to look at an application here where we're going to see force by pressing used to join two objects together, and along the way we'll discuss some other things we see. So a pallet comes into the station, locks in place, robot grabs the pinion gear and places it into the station, and then grabs a bearing race and places it onto the pinion gear. Okay, let's pause right there. Did you hear that? Did you see this big blue press push this piston down and force the bearing race onto the shaft of this gear? So this bearing race has an inside diameter. So that's a diameter like this. This is the bearing race. The diameter inside here is slightly smaller than the cylinder it was pressed onto. So this is the shape of the bearing or the pinion gear that this bearing race was pressed onto. So this diameter is just a little too small to fit on this surface. And so it actually has a little bit of a taper here. So it fits on easily, but then it hangs, and if you noticed, it sat just up here. But then this big press comes down with several tons of force and just crushes it down onto this diameter, which is a bit too large for it to fit. And so what happens is there's enough force in this press to actually make it go down onto it, but now there's a tremendous squeeze force where this outside diameter is being squeezed by this inside diameter, and that creates a lot of friction, and it holds this bearing race in place firmly on this gear. And so when you hear someone say it's a pressing operation or a press station, or they're going to join it using a press, that's what they're talking about. And there's so much friction, there was so much force involved, that's what the welling was. We actually heard the kind of a screech as metal ground against metal, and this was forced down onto that gear. A couple other things we saw in the video. We saw this is an air cylinder that came down and held this part in place. We see the switches that are used to detect when the air cylinder is extended and retracted. And we see a robot, which robots are always cool. So we'll finish up this video and then we'll move on. So the robot goes and grabs the gear out of the press, puts it into a testing station. All that motion you see right there, this rod is connected to an air cylinder, which is how this goes up and down. That hum you hear is a motor going really fast and spinning this gear to test it. Robot puts it back on the pallet, goes and gets the other bearing race and places it back to the pallet as well. And we're out. So that's a little bit about pressing operations or joining by force. And that's going to come up in this week's coming lab. Now, on to our discussion of ladder logic programming instructions. So this week we're, as I said, adding math and compare instructions. If you go on iLearn, you'll find the General Allen Bradley Instruction Manual. That has every Allen Bradley instruction available in the Logix Studio 5000 software. This is the set of math instructions that are available. It's in Chapter 6 of the manual. We're not going to go through every one of these instructions. We're going to pick and choose a few to talk through. But in general, if you ever need to, say, take the absolute value of something, there's an instruction for that in ladder logic. And you can go to the Allen Bradley instruction set manual and go to page 344, and you can read all about it and understand how to use the absolute value instruction. One quick note here. In this class, you're not allowed to use the compute instruction. The compute instruction allows you to type in whatever formula you desire, and it will compute the result of that formula. That's a great thing to be aware of and to be able to use if you were to be professionally coding PLCs. However, in here you're not allowed to use it because it sort of takes away from you having to think about how the PLC is going to scan the various math instructions and where you're going to store the result of those instructions. So in here, you're not allowed to use the compute instruction. Don't do it. Other than that, the rest of these functions are available for use. The function block diagram functions, you can't use them in ladder logic, so it doesn't matter anyway, and you can't function overload in ladder logic. So those are not helpful to you. The rest of these, absolute value through subtract, neglecting compute, are very helpful. So if you need to take the absolute value, add, divide, take the modulo, multiply, negate, take the square root, or subtract, these are the instructions that will allow you to do so. Now let's zoom in and take a look at actually what those instructions look like in ladder logic. So if you insert the add instruction into a ladder logic program, this is what you'll see. There are various operands here. So the white space you see for source A, source B, and destination. To the right of those you see white space. You have to provide an operand for each of these fields. So an operand can be a tag, or it can be an immediate value. So I could type in the name of a tag that holds a real or a dent or an integer, or I could type in directly a value. So I could type in the number 77.2 for source A and 21.4 for source B, and it's going to compute the addition of those. And you have to give a tag in which to store the result of the addition of source A and source B. The way that this instruction will execute is if the rung in condition is false. So if the rung in condition here is false, then it's just going to set the rung out condition to false as well. However, if the rung in condition is true, then it will take source A, add source B, and store the result in destination. As I said, these can be either tag names or immediate values. Destination must be a tag name. It has to have a place to store the result of this addition. Subtract is very much the same. If the rung in condition is false, then the rung out condition is false. So if what was true about add is also true about subtract, then we can either type in a number here, 77.2 and 27.1, or 35, any numbers that we want into source A and source B, or tag names. So operand 1, operand 2, if we had created those tags, we can either give immediate values or the name of a tag to this instruction in source A and source B. However, just like in the addition instruction, we must provide it with the name of a tag where it will store the result of source A minus source B. So notice here, this tells you what it's actually going to do, and it's pretty important. With addition, it doesn't matter the order, but with subtraction, it does. When the rung in condition is false, the rung out condition is set to false as well, and that's all that happens. It doesn't do any of the addition or subtraction for either of these instructions. However, if the rung in condition is true for the subtract instruction, then it's going to subtract source B from source A. So source A minus source B, and that is stored in the destination. Now I'm slightly glossing over something here, because we said this could either be an immediate value or a tag. But aren't there different data types? Like there's real, integer, double integer, referred to as dent, and others as well, like short int, sint. So all of these are different representations of numbers. Can it handle all of these? The short answer is yes. Yes, it can. So you can provide a tag that is any of these types, or directly input a number that is any of these types. So if I were to type in the number, as I keep saying, 77.2, that's a real. If I typed in just the number 77, well, that could be an integer, it could be a double integer, or it could be a short integer. An integer is a 16-bit integer value. A double integer is a 32-bit integer value. And a short int is an 8-bit integer value. Whereas real is a floating point real number. So yes, add and subtract can handle either immediate values typed in of any of these types or tags of any of these types. Now, however, that being said, what's going to happen if I say add 77.2 plus 3, I don't know why I drew a little line there, plus 3, and then store that into my tag. And my tag is a type int. So obviously, the answer to that addition is 80.2. But you can't store a real number in an integer tag. So what's going to happen is Allen Bradley is going to say, yeah, I'm not going to actually calculate the real value here. Instead, I'm going to drop the 0.2. So it's going to truncate the real number, add the 3, and store the number 80, not 80.2, into my tag. So the destination type can cause truncation if you're not careful. So if decimals are important to you, make sure you use reals for all your tag data types. If decimals aren't important to you, then you can get away with just using dent or int as your data type. Now, we don't have time in this course to do a full diatribe about the length of different integer, double integer, or short integer encodings and what the IEC or IEEE floating point encoding is. So if that is of interest to you, if that's something you want to look into more, please do. And it will certainly help you understand what's going on behind the scenes better. Here we have multiply and divide. We're going to go a little faster now because this is exactly like what we talked about in the add and subtract. You can either give an immediate value into source A or provide the name of a tag. The same thing goes for source B. Destination, you must provide a tag name. You have to have a place to store the result of multiplying A times B. If the rung in condition is true, then it will store A times B in the tag which is given as the destination. And it will also set the rung out condition as true. If the rung in condition is false, then it will not do anything to the destination and will set the rung out condition to be false. Divide is exactly the same. The only difference here is order matters a little bit, right? So which one is being divided by which? We can type in an immediate value or give a tag name for source A. We can type in an immediate value or give a tag name for source B. Immediate value is a number, right? So 77.2, that's a real immediate value. 20, that's an integer or double integer immediate value. However, destination must be a tag name. You have to have a place to store the result. If the rung in condition is false, the rung out condition will also be false. So if the rung in is false, the out is false. If the rung in is true, we are going to divide A, the source A, by whatever is in source B and store the result in destination. So be careful again with data types. If you want decimals in your answer, make sure that the tag you give is of type float and that your operands are of type float. If decimals are not important to you, then you're fine to use integers or double integers. Now there's a couple of notes associated with this instruction, note 1 and 2. Note 1 says if source B is 0, so if you try to divide by 0, the result is just whatever is in source A. So that's pretty nice. Rather than crashing the PLC because somebody accidentally did a divide by 0, instead it just moves whatever was in A into the destination. So that's important to know. If you accidentally divide by 0, it's not going to crash the PLC in Allen Bradley. Instead, it just moves A into source A into the destination. For integer destination and source operands, the result is truncated. So this is what I said. If you have an integer destination or source, then it's going to truncate. It's going to chop off whatever the decimal was. It won't round it. It'll chop it off. Okay? So be aware of that. If you do 3 divided by 4 and you're attempting to store that into an integer destination, the result will be not 0.75 because 0.75 can't be stored in an integer. And it won't be 1 because it doesn't round. It'll be 0. So 3 divided by 4, if you attempt to store that in an integer, will be 0. So this is multiply and divide. Now we're going to look at compare instructions. So we didn't go over, like I said, all the math instructions, and we're not going to go over all the compare instructions. There's a lot of them. And if you want to look into others that we didn't go over but that you're allowed to use, refer to the instruction manual on iLearn for the Allen Bradley ladder logic instruction set. So here we have another instruction which you're not allowed to use. It's the very first one. It's called the compare. So compare is sort of like compute. Compute allows you to type in an arbitrary formula to calculate the value or the result of that formula. Compare allows you to type in an arbitrary comparison and find out if it evaluates to true or false. You're not allowed to use it for the same reason you're not allowed to use to compute. It's too easy. You need to think and have to worry about the scanning order. So we have instructions for equal to, checking to see if two things are equal, greater than or equal to, less than or equal to. Limit is a bit weird. You don't need to use it, and you won't need to use it. You won't need to use actually any of these beyond limit. Mask equal to, not equal to, valid operators, and what is zero fill. You don't have to worry about any of those. But the 5 here, equal to, greater than or equal to, less than or equal to, those will be very helpful to you and important. Let's talk about just a few of those. So here we have equal. Notice it's very similar to the math instructions, just no destination, right? The reason there's no destination is because you're not storing the result of the comparison of A and B. Instead, what happens is, if A is equal to B and the run condition in is true, then the run condition out will be true. So just like with math instructions, this can be either the name of a tag or an immediate value. The same thing with source B. So either of those can be an immediate value or a tag name. The way this works is this is very similar to a contact. If the contact is associated with a tag that has the value true in it, then the contact allows the current to flow through, right? That's how we think of it. That's the analogy, the electrical analogy we use. The reality of the contact in ladder logic is that if the tag associated with the contact is true and the run condition into the contact is true, then the run condition out is set equal to true. That's precisely how this works. If whatever is here, an immediate value or a tag, is equal to whatever is here. So if we type in some tag name called my tag and this is your tag, this instruction is going to go to my tag and get the value that's stored there. It's going to go to your tag and get the value that's stored there. And if those are equal, and if the run condition in is true, then the run condition out will be true. And that's how this works. Notice there's a little statement down here about string compares. We're not going to be using strings and doing string compares, at least for the foreseeable future. So I included this little blurb so that you would understand what's going on. There is different functionality for if you're using this instruction and the operand is a string or if it is a number. For now, they will always be numbers. So in the rest of these, I will cut that out. So then we have greater than. I typed in GRE. It's GRT, greater than. This is not greater than or equal to, it's simply greater than. So this instruction works very much the same as this one. We can have an immediate value or the name of a tag in both of the operands, source A and source B. If the run condition in is true and source A is greater than, and it shows you that source A is the one that must be greater. If source A is greater than source B, then the run condition out is true. and that's exactly what it does. One caveat, if for some reason that either are NaNs, that's not a number, so if some garbage gets stored in one of these tags that you have given to these instructions, then it doesn't work. It will simply set the run condition out to false. So going back to the electrical analogy, think of it like this. If the contents of source A and the contents of source B are equal, then current will flow through this. But if there's no current up to this point, then there's not going to be any current over here either, right? Same thing here. Assuming that the rung is on up to this point, if source A is greater than source B, then current will flow through this and on to other rung conditions or potentially coils that exist over to the right-hand side of this instruction. These are very, very similar. We have greater than or equal to. Works just like greater than. It works just like equal to. It's simply the greater than or equal to comparison. So if the contents of source A are greater than or equal to source B, then the run condition out is going to be the same as the run condition in. So assuming the run condition in is true and source A is greater than or equal to source B, the run condition out will be true. This will conduct as long as source A is greater than source B. With the LEQ, less than or equal to instruction, if source A is less than or equal to the contents of source B, then this instruction will conduct. So if the rung in condition is true and source A is less than or equal to source B, then the rung out condition will be true. And that's what this says. Finally, there's one more class of trigonometric instructions that are related to the math instructions, but are considered a separate area in the manual. So we have the arc cosine, arc sine, arc tangent, cosine, sine, and tangent. So the usual suspects, right? These are the typical instructions that you would use for trigonometric calculations. So let's look at cosine and sine, just to make sure we understand how these work. So the sine instruction is very similar to the math instructions that we looked at previously because we have to have a destination. This must be a tag name, somewhere to store the result of the sine operation. However, there's not two operands, right? There's only one operand given to the sine function. The sine instruction takes one source. So if we give 0 to the sine, then it's going to give us the sine of 0 in the destination. Sine of 0 is 0. So if our source contains 0 either by immediate value, so if we just typed in the number 0, or if we give it a tag that had the contents 0, then it's going to store the value 0 in whatever tag we type into the destination. This instruction is only going to perform that operation if the run condition in is true. If the run condition in is not true, then it will do nothing. It will set the run condition out to be false, and it's done. So, assuming that the run condition in is true, it will take the sine of whatever is given in the source and store it in the tag, which is in the destination. The exact same thing is true of cosine. So if the rung in condition is true, then whatever value is given to the source, so either immediate value or if you have given a tag for it to go get the value out of, it will take the cosine of that source value and store it in the tag designated in the destination. So run condition in takes the cosine of the source, stores it in the destination, And for math instructions, the run condition out will always equal the run condition in. That's not true of compares, right? But given math instructions, the run condition out always equals the run condition in. If the run condition in is true, then the run condition out will be true. If it's false, then it will be false. However, the operation only takes place if the run condition in is true. Okay, so we're going to take a quick practical look at how to use math instructions in the PLC. And this is kind of important because it can be difficult the first time you're using math instructions or any instruction that you don't immediately see in the favorites bar. It can be difficult to find them. So let's pull up Studio 5000 and I'm going to use an existing project. We'll just use Lab 5. Taking a second, as usual. Okay. So here's the familiar lab layout. Create a new instruction, and I'm going to put a comment that says math instruction demonstration. So that tells what this is. Comments are important and expected. So make sure that you are appropriately commenting your rungs. So the first thing we want to do is implement a simple formula. What we want to do is we want to find the area of a circle. And we're going to store our parameters right in the local parameters for the main program. So first of all, we will create a tag called radius. And it defaults to dent. It always defaults to dent anytime you create a tag. So first of all, I'm creating tags, so I'm on the Edit Tags tab. But I'm also going to have to change this data type because I don't want it to be a dent. I want it to be a real so that I can have decimals. So we're going to need the radius, and then we're going to need pi, which we will also need to be real. So we're going to go into our main routine now that we've created, well actually hold on, we need to create one more. That's area, which will also be a real. So now back in our main routine, we can look through the different tags if we so choose. So we could scroll through and look for math. And remember, the formula for the area of a circle is pi r squared. The first problem we have is that pi doesn't actually contain pi. So we need to store the value of pi in our tag called pi. So let's use a move instruction. The move instruction allows us to take data and put it into a tag. Now this wasn't discussed in the lecture or shown on a slide, but it is exactly like any of the math instructions. You have a source, which can be either an immediate value or a tag name, and we have a destination, which must be a tag name. So we select this, and we see the various things that we could access from our tag table. We're not going to do any of that. What we're going to do is we're going to type in 3.14159. We'll have fun with it. 26535. There we go. All right. So we have our source, which is pi, and our destination is going to be pi. So now when this rung executes, it will move this value into our tag. That's our first issue. The second issue is we need to put the value into our tag called radius. So we need to put the radius into our radius tag. We could go up here and get another move instruction, but one of the great things is you can copy and then you can paste. So that's really helpful. So we'll just keep it simple. We'll say that our radius is 5, and we will say that we're not moving it into pi, but we're moving into the tag radius. Now let's add another rung. So I don't comment every rung. I comment sections of code. So here I'm doing my math instruction demonstration. So I'm not going to add another comment saying that. Rather, I just use the comments to show separation in the code. Up here, we were doing lab stuff. Here is the math instruction demonstration. Hopefully that makes sense. I'm going to show you another way to access instructions. So I could come up here to compute. So we have pi and we have our radius. So now we need to take pi times r squared. We could come up here, click the compute math tab from the instruction options when we scroll through, and we could do, multiply, subtract, divide, whatever. Another way you can go about this, though, is you can use any instruction. So we had the move already in our clipboard. You can double click the instruction, and what we need to do now is we need to multiply pi times r. So let's just type in MUL since we know the name of that instruction. Oh, there's the multiply. Okay. We wanted to multiply radius times pi. And I'm going to store it in area. And you're probably thinking, but wait, the area is not equal to radius times pi. It's equal to radius times pi. I know, just stick with me. Area. Now let's copy this instruction. Control C, Control V. Okay. Area now contains, as soon as this instruction executes, remember our ladder logic is going to execute from top to bottom, left to right. So this instruction is going to execute first, and it's going to multiply the radius times pi and store that in area. Now we need to multiply the contents of area by radius one more time to get to pi r squared. So let's type in area and radius into our multiply instruction. And we'll store that in area. Can you do that? Can you access the same tag as a source and as the destination? Yes, you absolutely can. So now let's download this program and let's see what we get for the area of a circle whose radius is 5. Yes, we will go back to run mode. Otherwise, nothing will happen. Oh, cool. Okay, so we move the value of pi into our pi tag. We move the value 5 into our radius tag. We multiply 5 by pi and store that in area. And then we multiply area by 5 and store that in area. You may be wondering, why is the value of area the same here as it is after we multiply it again by 5? The reason is because these instructions execute so fast that the screen on the computer can't actually get the information fast enough from the PLC to update this intermediate value. So it just updates the end of scan value. So 5 times pi, and then that value gets occluded because we modify it again. So what if we had a circle of radius 1, right? That should be just pi, right? Because pi times 1 would just be pi. So let's try that. So I double clicked this rung to make it editable, and you can tell it's editable because of the vertical row of eyes, vertical column of eyes. And then I made my edit, and then here is the finalize edits. It pushed in the edit. Oh, and look at that. Now we multiply 1 times pi, and then we multiply pi again times 1, and we still have pi. Yep. So our formula works. So we did well.